Good evening to all the participants for today's panel session. And we are here, we are about to start now. And I request our director, Dr. Annie Jacob, to welcome and introduce the speaker today.
Good evening to all our viewers. From KCG College of Technology, we have been organizing some amazing digital series, and this particular topic for today has grabbed a lot of attention. It's important for each one of us to gain some understanding of what the whole concept of cryptography means, the criticality of data. Privacy, protecting information, and having secure ways to communicate, this is where cryptography comes in and plays a big role. A quote from Bruce Schneier says it well. Cryptography in everyday life contains a range of situations where its use facilitates something as soft as your sibling trying to get some information from you, or it can be as crucial or vulnerable as the provision of a secure service data, like cash withdrawal from an ATM, pay TV, email and file storage using petty good privacy, PGP freeware, secure web browsing, and use of a GSM mobile phone. Imagine a lot of your personal data you disclose innocently can be misinterpreted or misused. So it is extremely important to secure your data, in fact, all of it. One can broadly classify the need here into two broad categories, personal and business-related data and communications. And this indicates the significance of cryptography as an essential in the digital era. It's my pleasure to introduce and welcome this expert speaker, Ms. Eliza Punnoose, for today's technical session on cryptography and data security. Eliza has 14+ years of experience in the financial industry, working for global leaders such as Capital One, JP Morgan Chase, Goldman Sachs, and Citigroup. Eliza's expertise in investment banking, consumer banking, and credit cards covers a range of advanced technologies, including payment cryptography, cloud services, Java systems, mainframes, and data warehousing. She is AWS Solutions Architect certified, CompTIA Security Plus, and also CSSE certified. Throughout her career, Eliza has had a passion for supporting women in technology and volunteers as a coding tutor at schools because she strongly believes that we should catch them young. She is based out of Chicago, and I know it's really early for you, as early as 6:30 a.m. in the morning. Thank you very much for taking some time off for knowledge bearing for the benefit of our students and all our viewers. Over to Eliza, and you're on.
Thank you, Dr. Annie Jacob, for that introduction, and also for inviting me to take this session for the students. And I would like to congratulate and recognize KC Tech for arranging for these webinars to help the students actually get an insight on the world outside of the college life. And with that, hello, everyone. And in today's session, I would like to impart what I learned in cyber, and I hope you will be a one step closer to more understanding of data security. Now, I remember it was during my first EMV project that I was introduced to payment cryptography, and I was totally fascinated by that. And I hope you will be too. So in today's session, I hope you all can see my screen. So in today's session, I would like to cover these topics. What is data security, why cryptography, what is cryptography, and so on. Let's break the ice with a quote from Eugene Spafford. So what he says is a truly secure system is one that is powered off and cast off in a block of concrete, sealed in a lead-lined room with armed guards. And even then, he has doubts about the security of the system. Now, if you look at it, for the organizations, they have their own data centers. Now, what are those? Those are heavily guarded buildings which have power grids and power lines running around with servers and devices that are stacked up and connected with network wires and with proper heating and cooling systems. Now, when we have moved to cloud technology, It's the same thing. It's just that we have shifted that responsibility to our cloud service providers like Amazon, Google, and Microsoft. So the security doesn't mean it's been handed over to them. We still have to take care of the security part using VPCs, the security groups, the S3 bucket policies, the ACLs, the IAM roles, the MFAs, and so on and so forth. And even with Amazon, they provide us with the KMS, AWS KMS, and the cloud HSMs, and even the ACMs, the Amazon Certificate Management. Now, let's start off with data security. It's very common. CIA triad is very common to all the people in data security. It stands for confidentiality, integrity, and availability. I'll talk about this in more detail in the upcoming slides, but I want to introduce the key terms in security. What exactly are those? The vulnerability, the threat, the risk, the exposure, and control. Give me 1 second, please. Okay, so what is this vulnerability all about? It is the weakness that you have in your system. It need not be the software application. It can be the hardware as well. Now, a threat, what does threat mean? It is the danger of exposing that vulnerability. Now, risk is nothing but the likelihood of that vulnerability to be exploited. Now, exposure is just an instance, okay, a time when that threat is actually exposed. And there are several controls or measures that we can take to reduce that risk. Now, in an organization, we actually weigh in that risk quantitatively as well as qualitatively to understand what risk is it, and to weigh in as to whether we should take any measures to remove that. We cannot address all the risk in an organization, but whatever is high, we take care of that, as well as mediums and low, whatever we could. So with that, the preventives, there can be multiple: administrative, technical, physical. Administrative is more like policies, separation of duties, job rotation, monitoring, and supervision. Separation of duties is more in terms of when I'm a security officer, I will not have access to the data because I'm responsible for the key management. But if I'm in the development side, if I'm on the development side, I will not have access to the keys. So that's what separation of duties is, and job rotation to make sure that there are no security breaches. Physical measures would be more in terms of the locks, the batch system, the biometric system, the man trap doors, the MFA devices that we have. Those are all physical measures that we can take. The technical would be more in terms of the encryptions, the IDS and IPS, which stands for the intrusion detection systems, the intrusion prevention systems, the antivirus softwares that are available, ACLs, that is access control list. For example, if you have stood up your own EC2 and you have attached a security group for it, the ingress and egress rules that you attach, it simply says that to my EC2, okay, I can only absorb or allow traffic which are mentioned in the ingress rules, and whatever is mentioned in the egress rules, only to those servers or endpoints I'll be sending data. Now, there are several standards and frameworks that are out there, ISO, IEC, DORAF, which is the Department of Defense. There is NIST, Security and Science and Technology, National Institute of Science and Technology, the ITIL, Six Sigma, CMMI, SOX. There are so many out there that guides the organization as to what needs to be, what is that the company or the organization has to do, okay? It's just a standard that that organization follows to tailor their organizational security needs. Moving on, why cryptography? It is an important way of achieving the data integrity, the confidentiality, user authentication, and non-repudiation. Cryptography gives us that confidence in our day-to-day life to actually perform that safe transmission. So whenever you enter your details, even if it's your name, your address, your tax ID, PAN number, or Aadhaar card number, you have to be cautious about, okay, the data that you enter, and you need to be confident about confident in that on that website before putting in your details, your credit card details. All that is important. So that is why we stress upon cryptography in today's world. When we connect to the internet, we are out there in the public, and anyone can access our system if not properly secure. Moving on. So when did cryptography actually start? Okay. It dates back to 2000 BC, when in Egypt, when the hieroglyphics were actually introduced. They used to write it on the tombstones. It was a starting point, and we had more like substitution ciphers, the Cytale cipher, Caesar cipher, Enigma machine, not to mention World War II, as well as there are so many options that are that over the years have been developed. For example, the Cytale cipher, if you can see onto your right, that is more like it's a stream of letters that are written on this a piece of paper, and if you do not wrap it around the right diameter, a rod with the right diameter, you will not be able to make sense out of that data stream of alphabets that are out there. So that's what Cytale cipher is. Now, in modern life, this is not what we are following. It is much more rigorous and much more complicated, so that we make it difficult for the hackers to actually get to our data. William Frederick Friedman is known to be the father of modern cryptography. Now, modern cryptography actually do not rely on the secrecy of the algorithm. If you look up the algorithms that I'm going to mention, it's actually out in the open. It's like open source. Why do we do that? So that it is out there for public scrutiny, so that it can be improved. So what is exactly going to be secret in modern cryptography? It's the key that we are going to use. So we need to ensure that the data that we have, even if it's a data at rest, data in motion, the data in rest would be like S3s, the data that is there in S3 in our servers or on our disk, data in motion when we are transmitting data in use, even the ones that we have that is being processed, that also we need to ensure that there is security around it. The TPM is one of the things that we have on our motherboard, which helps us with the security. Now, what is cryptography? The key terms I have already mentioned: the confidentiality, integrity, availability, and non-repudiation. Confidentiality. It's all about transforming the data into gibberish, which a middleman, or it won't make sense to another person if we do not have the right key. So it's transforming readable data, plain text, into a form which is unreadable, cannot be read, using a system or a product. It can be software or it can be hardware, like HSMs, the hardware security model. That is something that's hardware. The cloud HSMs, there are, even though we interacted using software, there is an HSM in the background which is actually doing that cryptography for us, or generating the keys or user keys or master keys for us. And it uses an algorithm, a cipher, which actually dictates how the encryption and decryption actually takes place. So there is a key, okay, and there's a key space. So if you're looking at the different options that are out there, the key space means what are the different keys that can be, that's defined for this algorithm. For a DES, which I'll be running through, it'll be 56 bits. AES will be, you might have heard of the 256 bits. That's the key space. Now, with that, what is integrity? Protecting the reliability and the correctness of data. Now, I'm sending data to my receiver. Okay, the receiver needs to ensure that there was no middleman attack, and the data was protected and it was not modified at all. So that is what integrity is. You do that using hashing algorithm. Now, with confidentiality and integrity, we have secured our system. But the most important thing is our service, whatever we are trying to secure, it's actually available for the outside world. So give me 1 second, please. Okay. Am I audible enough?
Yes, you are.
Okay, all right. So that's with availability. And what is non-repudiation? So the way that I am ensuring the recipient that I'm sending to is actually the person that I want to talk to in a communication. The receiver should also ensure that the data that it is receiving is from the person that it is claiming to be. So non-repudiation is a prevention of a sender or a subject from denying a performed action. That's what non-repudiation is. And all this can be done using cryptography. In cryptography, there are 3 other terms that are important, which is authentication. That is verifying the identity of a user. When I'm logging into a service or a hardware, it has to verify my identification. Okay, so that's authentication. Now, even with authorization, once you are in that system, you should only have access to those services which you are authorized to. In security, the underlying principle is need to know basis. You have given access to services only at a need to know basis and least privilege. When you get into an organization, you are not given access to everything in that organization. It will only be need to know basis and a least privilege. It's exactly what AWS defines as well. If you look at an S3, by default, everything is denied. Okay, and then you add access to whoever needs access to that S3 bucket. Same thing. So with authentication and authorization, when you are into or when you have access to a system, you need to ensure for the accounting. That's with the use of statistics. You have logging. It ensures that there is proper authorization control. It gives data to billing, trend analysis, resource utilization, as well as capacity planning. Now, let's introduce crypto systems, which is symmetric cryptography and asymmetric cryptography. And what is symmetric cryptography? It's like our old days lock and key. You have a lock, you have the key to open it. And if you make a duplicate of that key, yes, you can still open that lock. That's what symmetric cryptography is all about. There is one key, and using only that key, you can unlock and lock the data. Asymmetric cryptography is about a different kind of a lock, and it has 2 keys. So what that does is, if you want to encrypt or decrypt the data, for one process, you need to use one set of keys, and for the other, you cannot use the same set of keys. You have to use the other set. So private and public key comes into picture. So if you lock your data with the private key, you can unlock it only using the public key and vice versa. All right. So symmetric key is also known as shared secret cryptography, private cryptography, and asymmetric key is known as public key cryptography. Okay. Now, why do we have 2 crypto systems? Okay. There is a reason for it. There are some differences. The symmetric cryptography is known for its speed, okay? That's its core strength. But there are several weaknesses that are attached to it. The distribution, key distribution. Now, physical keys, I mean, if you have a key, if I have to communicate to somebody in India, all right, how do I distribute that key? How am I going to pass that key? That is a challenge. No non-repudiation. So if I'm having a symmetric key with somebody in Egypt, all right, I will not know the data, the origin of that cipher. Okay, is it coming from the person who is in the US, or is it coming from the person in Egypt? So that is what is no non-repudiation. I will not be able to recognize the origin of that. No scalability, meaning if I have to talk, let's say A have to talk to B and C, we need to have a key pair or the key which has to be shared between A and B, A and C, and B and C. Okay? And it cannot be shared with the other parties. So that's what no scalability is about. Now, if the key gets compromised, it has to be regenerated. That's with public key cryptography as well. But the processes or the complexity is more for a shared secret cryptography. Now, with asymmetric cryptography, the strengths are key distribution, all right? It's easier. There's a private key, there's a public key. I'll touch upon it in the upcoming slides. Now, the authenticity, you can verify that. Integrity, okay? That also I'll touch upon later. Non-repudiation. Scalability. Those are the strengths. Now, weakness is the speed. So in actual world, we use a hybrid cryptography. We use symmetric as well as asymmetric cryptography for our communications and in the internet. Now, common symmetric cryptographies. We have DES, 3DES, and AES. DES stands for Data Encryption Standard. So if you look on the left side over here, it is a 64-bit plain text. So if you have a file, it is chunked into 64-bit text, all right? And then the key, in DES, it's a 56-bit key, but it is turned to a 64-bit key using the parity bits, all right? Now for the 8 bytes that we have. So what you see over here is the ECB, the mode of operation. It's called the electronic code book. So what it means is the plain text gets chunked into 64 bits, okay? And it gets into our encryption module or the DES algorithm, and you applying the key, it gets translated into a 64-bit cipher. And that gets repeated for the next 64-bit plain text. Now, if you have a file which doesn't fall into the 64-bit chunks, then we use parity. That's what ECB is about. CBC is about, I mean, so what we say, what we can understand from that is, for example, the plain text, the 64-bit. Let's say it is Eliza, all right? There are two texts which is Eliza and then followed by another Eliza. So the cipher block that you get out of this, it's going to be exactly similar to the next one because I have the input as Eliza and Eliza. So that is why we have the cipher text coming exactly the same, and that is not considered secure. Okay? It needs to have some randomness to it. That is where the others come into picture. Other modes, CBC, which is the cipher block chaining, the counter mode, the cipher feedback mode, as well as the output feedback mode. One thing that you need to note for electronic code book, as well as the CBC, is it's a fixed bit. So over here, it's 64 bits, okay? It has to be fixed bit chunks that we are working with. In CFB, as well as OFB, we have a chance to change that, all right? We can truncate it based on the algorithm. CTR is a counter. We introduce a counter, and then we increase the counter for every chunk. So there's a counter out here, okay? For every chunk of data that we are going to encrypt, we add a counter to it. Let's say if we start with 1, for the next block that we are going to encrypt, it's going to be 1 + 1, 2. And it goes, it goes on like that. That's what CTR is, which is the counter mode. Now, for CBC, CFB, and OFB, the underlying logic is whatever you get in our first, your plain text is there, but you introduce a randomization with the previous ciphertext that you have created. So if you start off with, for a file, there is no previous ciphertext that is available. In that case, we use a initialization vector, all right? That is introduced over here. There is a plain text. It goes through our encryption process. We get the ciphertext. Now, this block acts as the initialization vector for the next block. It goes through the same encryption, gets the ciphertext, and it goes to the next block as a chain. So that's what the chaining is all about. It provides a randomness that we require for our encryption. Now, I talked about DES. The requirement there is 64-bit blocks. And also, the key that we are going to be using is 56-bit key plus the 8-bit parity, right? With time, we understood that DES is not that secure. We moved on to 3DES, and that is still being used in the payment industry. Now, 3DES or triple DES, as we call it, what that means is there are 3 keys that are being used, okay? There are 4 variants for it. I'll get to that. So 3 different keys, and it's a combination of encryption and decryption that we use within that algorithm. So for example, and again, for 3DES, what that means is we have 56, we are looking at 168, okay, bit key that we use for 3DES. Now, if you have a plain text, okay, the key is divided into 3, okay? So the plain text goes into the first algorithm, all right? The first part of the key is getting applied, all right? And that gets into the next set of key, which is the second part of the key, okay? Again, the DES algorithm is applied to it, and it goes to the third part of the key, and that gives, the output of that is a ciphertext. Now remember, we had the 64-bit block in the beginning. So from here, we get 64-bit block and we get a 64-bit ciphertext, which has gone through the 168-bit key. Now, the 4 variants that we have is, now we can have 3 different keys in 3DES. Okay? Now, 3 different keys using encryption all the way, all right? The second variant would be 3 keys, but the second operation that's going to happen, it'll be a decryption, okay? Now, for the third variant, it is 3DES 2 key. What that means is we use only 2 keys. There is a K1, there is a K2, and we reuse the K1 in the third set of operations. Like the second variant that I mentioned, the fourth variant will have a decryption instead of encryption in all the 3 steps. So there is DES and 3DES. Now, the most common right now what we have is the AES 256. In that, we are looking at 128-bit blocks. Okay, now there are various key strengths. We have 128, 192, and 256 bits. In the industry standard is definitely 256 bit because it is more secure. Why is it more secure? Now, we are looking at 14 rounds of encryption with AES cryptography. For 128, we have 10 rounds of encryption. 192, we have 12 rounds of encryption. But with 256, we are looking at 14 rounds of encryption, which makes it very, very secure. Now, you might be asking about what are the algorithms? What does the these algorithms actually do? What is the math behind it? It's out there in the public that I mentioned. In modern cryptography, that's what we believe in. But you can look it up. But for me, I do not deal with what the cryptography algorithm is all about. I deal with the actual usage of those algorithms and the generation of the keys. I mentioned earlier that the distribution of cryptography is a challenge. Now, offline cryptography, what that means physical distribution of that key. So if you have a key that you want to share with, the party that you want to communicate with through mail or actually physically delivering it, that's the only option that we have. Now, with public key encryption, which is what I mentioned about hybrid cryptography, using public key encryption, we can actually transfer that data, that key from our system to our recipient. That's what a TLS communication or the HTTPS communication that we use on our daily basis. That's what is happening. Now, Diffie-Hellman is another scientist who came up with a way, it's very similar to public key encryption, and it is the grandfather algorithm for that. It uses 2 prime numbers for coming up with the key. Now, you'll be asking why prime numbers are so difficult. I mean, it can be easy to crack. Actually, it is not. It takes, if it's a large prime number, and the product of those prime numbers, the factorization takes a lot of time. So that is the reason for the Diffie-Hellman to be a success. Now, storage. Never store key where the data resides. So being a key officer, you can never get access to the data because you are managing your keys, right? And it's same with the development or the development side. The technical developers do not have access to the keys. What is key split? Now, when I generate a key, I do not store the key as is. I divide that, I partition that key into its components. That's not like dividing, if it's ABC, I'm not dividing into A, B, and C. No, that's not what goes into that. It's divided, it is actually partitioned or split into components, and the key officers keeps one component and they are responsible for safeguarding that component. To generate a key, to actually find what that key is, which is the whole fundamentals about securing our system. To bring that key, or to understand what that key is, you need to bring all the 3 components together. So compromising a system when, by the way, the key can be split into not just 3 components, it can vary from 2 to, I think it can go up to 9. Okay, so only if 3 components come in together, we can form 3 components come in together, we can form the key. So that is why compromising a key is going to be challenging. You are very well aware of the AWS KMS. It's a service that is provided by AWS. You have AWS managed keys, customer created keys, okay, who has their account on AWS. Now, using those, we can create keys. 256 bit keys is what we are looking at. Now, what is that? Can we see that key in AWS? That's the only challenge. We do not get to export that key out. We reference that key using the key ID. Okay. So that is with AWS. Now we have cloud HSMs also in AWS. Again, you have you can access through the software that are available and create your own keys or access your keys, and you can perform several key officer duties with cloud HSMs as well. SafeNet Luna HSM is one of them by Gemalto, and you have other payment HSMs as well, which are out there in the public that the payment industry uses. Now, moving on to common asymmetric cryptography. There are common ones are RSA, you are familiar with, Elgamal, which is actually based out of the Diffie-Hellman algorithm, the elliptical curve, that's another one. Now, all these cryptograph systems, there are many more, but some examples that we use in our day-to-day life is PGP, okay, pretty good privacy, TLS, transportation layer security, our HTTPS communication that we are using, SSHing to a server, or even the secure multi-purpose internet mail extensions. And there are plenty more that are out there. Now, I want to show you something about how to generate your own key. You might be wondering, I've used this to create a key. Let's just use OpenSSL for that. Okay. Now, gen RSA. I want an RSA. I'm creating an asymmetric key, a private public key pair. It's a gen RSA. Okay. I'm going to put test3, and I want it to be out into my okay. And I want it to be a 248-bit. And now you have to attach a passphrase to this. Okay. So if I show you, see, I've just created the private key. All right. Now, that's the private key that we have generated. Now we want to create the public key as well. Okay. So for that, we'll be using, okay, and what do you want? That's the private key that we just created. Okay. And you want it in the form of hem. Okay. That's another format of how you want the key to be. And you want the public key out, and you want it to be out in the pub .key. Okay. So if I go back, I've just generated the public key as well. So let's open and see how it looks like. And by the way, if you have a Mac, it's much easier using Homebrew or something. You can actually create, you can even use GPG for your so that's how a public key looks like. You can see that. Okay, it says public key in it. And let's open the private key as well. So it gives you what you have. It is the RSA key. You have DES. You have used the CBC for that creating the private key. And this is what you can't make any sense out of this, but this is how you can create a private and a public key pair. Now, we will be using the certificates. I'll get to that when we reach that point. Now, with cryptography, let's move on to integrity. Now, integrity is all about not ensuring that the data is not changed. Now, you can use, it's just hashing. Okay? We have several hashing algorithms. You might be aware of MD2, MD4, MD5 is what is mainly used now. There is SHA, there's SHA-1. Industry standard is SHA-256 now. There are other SHA versions as well. We have 224, we have 512, we have 384, there's 512. The difference is in 256, we are using a 256-bit message digest. So what that means is we are outputting the digest, okay? The output of this is going to be 256 bits, okay? The same thing for SHA-512 and 384, it actually uses 1024 bit block size. MD5, it uses 128 and processes a 512-bit blocks. So that's what are the different hashing algorithms that are out there. HMAC is another one. It also gives us authentication code. Now what, let's go ahead and try creating a message digest, okay? Okay. And let's say I want SHA-256, okay? I think I had a file which was in temporary folder. Yeah. Look at that. It just gave us the hash for it. The same thing that you can use for MD5 as well. So I would encourage you guys to, we have seen the integrity SHA-256. I would encourage you guys to look at MD5, how we can do that using OpenSSL, or if you have a Mac, try GPG. And also you can, with the key pair that you created, you can try encrypting a file. That would be something that you want to try it out today. Now, moving on. Now, integrity gives rise to digital signatures. So what is a digital signature? It relies upon public cryptography, and it assures the recipient that the message truly came from the sender. That was non-repudiation, and the message was not altered. Now, what that means is, if I'm sending a data, A sends to B, what A is going to do is, it is going to encrypt the data, or it's going to sign the data. The term is sign because we are looking at digital signatures. It's going to sign that data with its private key. So what that means is only A has access to its private key. Private keys are never shared. So it has access to its private key, and when it sends to anybody out there in the public, it can only be decrypted using, or it can only be verified, decrypted / verified, using that public key pair corresponding to that private key. That assures you that the sender is who he claims to be. And if we are able to decrypt it or verify it, it means that the message has not been altered along the way it was transmitted. That's what digital signature is all about. It's simple. It's just public key cryptography. We are using the private key instead of the public key. So maybe I did not touch upon this. The confidentiality, or when we are encrypting, what we need to ensure is the public key of the recipient. We encrypt our data with that public key, and then we send it to the recipient, so that when it reaches the recipient, only the recipient can decrypt it, because the private key is safely stored within its within that system. It is never shared. So in cryptography, within cryptography, we ensure that we encrypt the data with the public key of the recipient, so that only the recipient can decrypt it. In terms of signature, we use is the private key of the sender is being used to sign it or encrypt it, so that using the public key, anybody can decrypt it, okay, which verifies the non-repudiation as well as the identity of the sender. Now, this brings us to the PKI, okay, public key infrastructure. So why do we need that? We have a private key and we have a public key. We need to ensure that the sender who claims to be xyz.com, it is actually xyz.com, and it's not a middleman imposing to be xyz.com. That's where PKI, or public key infrastructure, comes into the picture, where we have created a system wherein we can trust each other with the help of digital certificates. Okay. We might be aware of X509, the certificates that are being sent out there is X509 standard. And it's actually started for telephone services. You might be wondering how it is actually being created. So digital certificate is all about when we send, or an entity who wants their public key to be certified, okay, to ensure that anybody who wants to communicate with XYZ can trust me, saying that, okay, yeah, XYZ is legit, okay? So that is why we use digital certificates. What we do is, let's do it using a picture that I have drawn. So let's say I'm an entity, xyz.com. So I start off with my process creating a key pair, like how we just created. Now, if you look at Google. Now, how do you see what is the certificate? What is its certificate? For YouTube, if you click on this, okay, you have the certificate, okay, and the hierarchy or the chain of trust, okay, is seen using this. Over here, you can see that for google.com, the intermediate CA, so it's just acting on behalf of the root CA. We have GTS CA 101, and also the root certificate in this case is the global sign root CA, right? So let's just say me being an entity, I want to register my certificate or register my public key. So I create a key pair. I send that to the intermediate CA, let's say GTS CA in this case. I send it to GTS CA. And what GTS CA, what am I sending to GTS CA? My public key along with a CSR. That's called certificate signing request. Okay, the certificate signing request contains our public key of xyz.com. So I send it to GTS, and GTS identifies or identifies xyz.com, ensures that yes, it is legit, it has come from xyz.com. It actually does that, like the police verification that you have for passport. So when you apply for a passport, you have somebody from the police station actually coming to your house to ensure that yes, the person who have claimed to be here actually lives here and the identity is verified. Similar to that, the intermediate certificate verifies the identity, and it creates an SSL certificate, okay, which is the public key and information regarding who has signed it, what encryption has been used. You look at this. That was for intermediate CA. Okay. It gives me, okay, this is the issuer of the intermediate CA is the global sign, okay? And this is my subject, which is my entity, okay? This is the public key that we have generated, and several other details regarding the certificate is there, is provided. Certificate is actually the public key. So we have that. Now it creates a hash of that certificate that we just created. Okay, hash is like message integrity that we looked at. Now that hash is signed by the private key of GTS, which is the intermediate CA. So it signs it. And then the SSL cert for xyz.com is created. Now, along with that, now our browser, or whenever I'm going to access xyz.com, I do not have the GTS CA with me, or the intermediate CA's public certificate with me. So the intermediate certificate also comes in, will be sent, which is the same thing as xyz.com. The SSL certificate of GTS, which is its public key, that is signed by the global sign root CA. Similarly, we'll create a hash of this certificate, which is signed by the global root CA. So if you look at it, we have lots of root certificate, and geo global root certificate is one of them. Okay, so that is what we are, the root certificate is there embedded in our browser, which verifies the authenticity of the certificate. Going back, so both these certificates, that's from for xyz.com as well as the GTS CA, is being sent back to xyz.com and kept on their server when we request for a certificate signing. Okay, so that's what happens once a certificate is issued. Now, when I actually want to communicate using my browser, okay, xyz.com, what happens is xyz.com actually sends back both these certificates. Okay, that is the xyz.com public key certificate, as well as the intermediate CA's certificate as well. So what does a browser have? Browser doesn't have any knowledge of, either of them, xyz.com nor GTS CA ICA, but it does have the global sign root CA. So it starts with that. It has a public key for global sign root. Please make note that private key is never shared. So when the browser gets these certificates, it starts off with this certificate that we have, that's the intermediate certificate. Using the public key that we have for the global sign root certificate, the hash that we have, which has been signed by the private key of global root CA, we can decrypt it, okay? And that we will help us open up the SSL certificate, which contains the public certificate or public key of the global of GTS. So one more time. So browser has the public key of the root CA, which is used to verify the signature, okay, creates the hash of the global root CA, which gives us the GTS certificate, which contains its private key, its public key. This GTS public key is what we will use for our next step for XYZ certificate. The public key over here comes over here and we decrypt the hash that we have been created because it was signed by the private key of GTS-CA, and that will help us open up the public our public key, which is contained in the SSL certificate of xyz.com. All right. That is what our browser uses. Now we have the public certificate of the public key of xyz.com. Now using that, what our browser does is for a communication that is being sent, our HTTP request, okay, it randomly creates a symmetric key. Remember, the advantage of symmetric key is its speed. So it uses this public key that we have for xyz.com, which has gone through all this decryption process. Now, that public key we use to encrypt the symmetric key that we just randomly created for our communication with xyz.com. And that gets sent to xyz.com. What's the catch there? Now, only XYZ will be able to decrypt it because only XYZ has its private key. So for any further communication, that is where we have established our session, okay, where we have successfully transferred the symmetric cryptography key that can be used in our communication. Now, cipher suits are more in terms of when a client talks to a server. The client actually tells the server that, okay, you know what, these are the cipher suits that I can use, okay, or I have access to. I'm using TLS 1.2. You know, I can, my exchange algorithms can be RSA. That's what we just saw for all this communication. RSA, it can be elliptical, it can be Diffie-Hellman, or any of those. And for digital signature, I'll be using, again, the public cryptography is what we need for digital certifications as well, digital signatures as well. RSA, elliptical, whichever it's the server chooses. It's actually an acknowledgement between client and server. And client gives, these are the possible cipher suits that I can communicate with you. And the server just uses one. Bulk encryption is what the symmetric key that we have generated when I'm using the browser. Once we have decrypted and we have the public key of xyz.com, I have to create that symmetric key. That is what this shows up. Now, message authentication code for any integrity, it uses SHA-256 or any other hashing function. So what we have seen in our example is over here, is the hierarchy of trust, okay? The hierarchy, the certificate chain, okay? The root CA is this is the intermediate CA, and this is our actual end destination. We can also have signing CAs. We have self-signed CAs that will be used within an organization. If any public communication, of course, we'll be using root CAs for any transfer of data. Now, CRL is yet another concept. It is just certificate revocation list. So if a certificate has been revoked for a company, it's actually stored in CRL. So anytime browser establishes a communication, it actually checks the CRL as well to ensure that certificate that we just received has not been revoked. So that's all about PKI infrastructure, okay? And I did mention that I'm going to show you about how to create a certificate signing request. So let's do that. Key. So we had it at pvt.key, and let's out c new dot, let's say CSR. Maybe. Okay, so this is what for the authentication, when it's issued, it actually has to give all this, and you have to give the information about the about yourself, the entity, the x5c.com. In this case, x5c.com has to give information about the country name, the state. This is where X509 comes into picture, which is, you know, in more in terms of how the telephones worked at that point. Let's say xyz.com, and okay. So with that, a certificate has been created. As you can see in new CSR, let me open up using. So as it says, is a certificate request. Okay, and this gets sent to the intermediate certificate. All right. So I hope I have covered some basics of cryptography, which included the confidentiality, integrity, non-repudiation, the PKI, and I hope that was interesting. And I also want to urge you during these trying and unprecedented times to brush up on several topics that are very industry related, and some topics which interest you, for example, cryptography. And keep your minds open, and you never know, you might discover something that you end up being passionate about. And it's a very challenging world, and unless you update yourself, it's actually difficult to keep up with the emerging technologies. And nowadays, if you ask, everybody wants a full stack developer. That's what's in demand. And I also want to touch upon one thing that Dr. Annie Jacob mentioned in my introduction, that I support women in technology. I see that in my day-to-day, like that many women colleagues on the technical side, they eventually move out of technology and they take up non-technical roles. But I want to call out to all the women who are attending this call that, do not shy away from this opportunity. This is challenging and it will always help you. Now, before I close, I want to touch upon the next steps, which are for your undergrad or postgrad. These are the courses that you can take. There's a bachelor's in cybersecurity. There are specializations that are out there. Master's in information, cybersecurity, if you want to go for your postgrad. There are even certifications. AWS provides the specialty certifications for security. There's CompTIA Security Plus. There is CISSP. There is CCSP, that's Cloud Security Professional. If you are more into hacking, certificate and Certified Ethical Hacker is another one that you can go for. Now, what does your career in cyber look like? Now, cloud is so emerging that cloud governance is very, very key in today's world. Now you have it's information security officer, application testing, penetration testing, black box testing, white box testing. Okay, those are what that comes into application testing if your interest is in that. Vulnerability management, weighing in on the risk. What are the vulnerabilities in an application? Again, cryptography, my area of expertise. It can be non-payment as well as payment cryptography. Both of them are a little different in terms of the PCI, the payment card industry. It's a little different than non-payment side. Again, endpoint security. That's more like your laptops that in an organization you have to ensure that the endpoints are secure. Risk management is another one. Audits. There are so many options out in cyber that you can look into. And with that, I would like to close my presentation and open up for any questions. Thank you, everyone.
Thank you so much. We have quite a 6 to 7 questions here. If you're okay, can I read the questions to you?
Oh, absolutely.
Yeah, okay.
Hopefully I can answer.
The first question is from a first-year student, Karan. He wants to know whether compress data and encrypt or encrypt data and compress. Which way would you recommend?
Compress data and encrypt. I would say compress data and encrypt. At the end of the day, security is not about one layer, okay? It's a layered security. Now, if you put something in your S3 bucket, okay, you want to ensure if you're using S3 bucket has an option for encrypting with server side, or you want to use an AWS KMS, or even the customer managed keys as well, your own keys. Now, with that, I would say you can use, you shouldn't just rely on AWS. You should have some other cryptography, and layered security is what we should be looking at. For example, you can encrypt your data with a PGP key or even a symmetric key and then put it into S3. So I would say compress it. That's what I have done in my job. I compress the data and then store it, and then encrypt and store it. Layered security is very key in that process.
Thank you. And one from Dr. Jay Kumar. He wants to know when we should use symmetric cryptography and when to use asymmetric cryptography. Can you also tell about Blake 64 algorithm? Okay.
So when can we use symmetric cryptography? So for example, so I would say the ideal word would be to use hybrid cryptography. An example is TLS communication. You cannot just rely on one, because there are advantages for one cryptography over the other. So weighing in on the advantages and disadvantages, you need to make that decision. Now, in terms of payment cryptography, there are several times where we use symmetric cryptography. Okay, the reason why we use that, again, speed is a key factor, but there is no outside communication that's happening. That's a reason that we can solely rely on symmetric cryptography. Now, if I have to deal with outside world, I would definitely be using asymmetric key. But again, speed needs to come into picture. Now, that's where hybrid cryptography will be used. A combination, so that once that identity or the authentication has been established, then we can share a symmetric key so that the speedy transfer or communication can happen. So, you mentioned about an algorithm. So let me put it this way. I do not deal with algorithms, and in modern cryptography, algorithms are open source. So you can definitely look that up. I'm not familiar with it.
Yeah, in fact, the next question is related to that open source. They are saying in online, many decode opinions are available. Is it possible to decrypt this certificate using that?
Decrypt a certificate. Now, certificate, why do you need to decrypt? Because it's already open. We already have the public key information in that certificate. So is it possible? If we are looking at quantum computing, can we go back to private key and break it? Yeah, why not? But In the current world, it's not possible. Otherwise, it would have already been done. But that's where we have, with the advancement of quantum processing that's coming up. And on the side, we also have quantum cryptography be passionately looked into to ensure that we keep up with that quantum computing and we don't compromise on the keys. So, yeah.
Thank you. And one from Mr. Sadasivam. How the threats to cryptographic system can be prevented?
Oh, how threats to cryptographic systems. Now, layered security. Now, like I mentioned, for example, now, if I'm looking at a key that we use, I do not have access to the key. I don't have the whole key with me. I divide that into components. Okay. Now, each component is actually with one key officer. And now, again, that is secured. It's safely kept, put away so that nobody has access to it. So there are several layers. It's not just I create a key and leave it. No, it will be divided into components. And then to access that, you have to put all the three components. If I'm dividing into three, all the three components have to come together to form the key, which will further be utilized. So layered security comes, for example, if you have your data center, it's heavily guarded, okay? In order to get it, only authorized people can get into it, get to the data, get inside. Even if you manage to get inside, to get to your hardware devices, that's another total different protocol. So that's what AWS does, and that's what traditionally other organizations did as well. Layered security is the way to go for prevention of all these threats.
Thank you. So the next question is related to what you were talking about now. Aida wants to know if the key can get corrupted. If yes, can it be easily retrieved? Of course, it's kept safe, but she wants to know if the key gets corrupted. Can the key get corrupted?
Oh yeah, definitely. Key can be compromised. That's where regeneration of the key comes into picture. And key rotation is another thing. I touched upon that in one of the slides where symmetric cryptography, okay, that's one of the disadvantages. Key rotation, key replacement, key regeneration, however you want to term it. It's a little more challenging, but if it gets compromised, anything can happen in this world. Okay, if it gets compromised, our process would be to regenerate that key and then use that key, discard the other key, totally discard it. And the systems that have been in the older system, you have to align it to the new key that we generate. There is a way we can do that as well.
Okay, thank you. And from Mr. Rajula, is cryptography the best security option for IoT devices? If so, which is a better crypto system, symmetric or asymmetric?
Again, I would go back to my answer I gave earlier. There is no set answer to, okay, symmetric or asymmetric key is the best option. You have to weigh in on several other parameters to actually come to that. IoT devices, it's like the public encryption. When you talk to something in the on the internet, what are we looking at? We need to ensure that the person that we are talking to, who is claiming to be, the certificate comes into picture. Okay, the non-repudiation comes into picture. Once that we have established that, okay, we are talking to the right person, then that's where non-repudiation, all that is primary. That's primary over there. Then it kicks in, okay, we need to ensure that the communication is speedy, it's fast communication. So we end up actually sending a generating a symmetric key on the go and use that symmetric key for further communication. That's what TLS actually does. Same thing with IoT. It's a hybrid cryptography world. It has to be a combination of both for any communications which is related to the internet.
Thank you. And next question is also from Karan. With increasing popularity of Let's Encrypt, scammers do get SSL certificates. Is it now recommended to ask people trust website that has an SSL certificate?
Okay, so SSL certificate, if the CA, root CA is not compromised, then yeah, we can trust it to an extent. There can be hackers. There are ways that they can hack into the system or hack into communication. There are ways that we can identify. That's where the intrusion detection, intrusion prevention system, cryptography on its own, you know, if you look at data security, it is one important portion of data security. But there are several other systems that come into picture. For example, the one I mentioned, intrusion detection, intrusion prevention, antivirus, authentication, all that comes into picture for final security of the system. So if somebody hacks into it and if the security or the certificate is compromised, then the organization should be prepared for it. Detect that, logs, logging, tracing, okay, the communication, there's a pattern which is not, it's irregular. You actually isolate that into a botnet. Okay, isolate that into a honey net is what we call it. And then understand that pattern. Everybody comes up with a new way to hack a system. So that's where honeypot system comes into picture, so that the system or the organization that gets impacted will be able to understand this new attack. I mean, there are several systems that prevents it. And we have, if it's something new, you know, that's how we go about it. So if a certificate can get compromised, I will not vouch my money for, you know, it never gets compromised, but it will.
Thank
you.
It
won't.
Thank you. And next question is from Dr. Krishnamurthy. In security, are standard and framework the same?
No. So standards is more like a policy, or how can I put it? It's you know, like the ISO standard, you know, it has to meet some criteria where it says that, yes, you know, yes, it is approved. Or if you look at PCI DSS, there are some standards that we need to follow. And if we meet that standards, yes, you know, we are eligible. Now, framework is more in terms of, it helps an organization align itself. It's just it's like the Spring framework, okay? It's just, what can you say? A baseline on which we can build upon. Once you build upon that baseline, that's something that you can use and build on top of it. So standards, it works hand in hand, but framework, it's not exactly the same concept, but yeah.
Thank you. And he has another question. Which is better, Open SSL or Open SSH, and under which situation?
Okay, SSH and SSL are going to be different. SSL is, you know, our open protocol, as in like the communication that SSH is more in terms of the 22 port that we're looking at. So it's for two different purposes. So, yeah.
Thank you. And next is too technical. Does law of diminishing returns apply when specifying iteration to PBKDF2, bcrypt, argon2i, or similar algorithm?
Oh, wow. You know what? I do not have an answer to it. I do not know what that is. So, but, you know, I can look it up and I can get back to you on that.
I'll ask him to connect with you through LinkedIn,
Okay.
you know, to get the answers. Thank you. And if you were saying for one question about key and data, you know, stored in different places. So Mr. Arunachalam has posted a question. If key and data are stored in different places, how does it work in an end-to-end encryption like WhatsApp?
Okay, it's stored in a different way, in different system, but if it's stored in a different system and it never communicates with each other, then there is no secure communication coming into picture at all. No, that's not what I meant. What I meant is access to the data and access to the keys is going to be separate. So being a key officer, I have access to keys, okay? I do not want to put the data and key, I should not be getting access to data and key to put it together, because that's what it is important, right? If you have data and key together, there are many options that are possible. So that is a segregation that I was talking about, segregation of duties. So me being a key officer, I will not have access to data. But if I'm a developer, I will not have access to the keys. Okay? Now, that's why key is getting split as well. So to actually encrypt something, if you look at AWS KMS, for example, or Cloud HSM, your application system makes a call. If you have it on an EMR or EC2 or application endpoint, okay. If your system, when it accesses the AWS KMS through a KMS key ID, it has access to the key ID. The data has access to the key ID. Okay, it encrypts it and puts it out. At that point, the developer has only access to the key ID, doesn't have access to the key. Okay? Key ID and key are two different things. That's why I mentioned that in KMS, you cannot export the key. Okay, so you can encrypt or decrypt your data using the key ID. Okay, at the same time, the person who is using the AWS KMS who manages that, the team who manages that, they do not have access to the data that is being used for that encryption. They only manage the keys. So even if you look at Cloud HSM, there are different sets of users. There are crypto user, there's a crypto officer. So the separation of duty also comes into picture in terms of key management as well. So everything is divided, segregated in such a way that one doesn't overlap the other and give way to decryption or even any breach. So.
Thank you. And one last question. Among CAA security principles, what are their levels of attainment in blockchain applications?
Okay. I do not deal with blockchain. Is a crypto coin that we are talking about, or what's that blockchain? Is it the CBC blockchain code? I want to understand that.
Yeah. And she has one more question also. What is the optimum key size you recommend for RSA to balance computation and performance?
Okay, industry standard is 2048. Okay, the longer the key, the better. But we also need to ensure that the communication is speedy. Okay, that's one advantage that one factor that we need to understand. So 2048 is the standard right now. So I would say that.
And a few other questions are there. I think you have answered for all the other questions in your earlier questions, in your earlier answers. So I think we are done with all the questions. And thank you so much, having on a Friday morning, spending time with us. And for a wonderful session. There are so many in chat window as well as in Q&A. Many of them have posted that it was a very nice presentation. They have shared their feedback also. Thank you so much. Thanks again.
Oh, thank you, Devasundari.
Eliza, on behalf of KCG College of Technology, thank you very much for a well sorted out session. Thank you.